Right, so welcome to the 13th lecture on random processes. Um, what have we discussed last time?
Family of random processes.
Yeah. So some statistical descriptions linked to random processes, right? So the statistical descriptions that we looked at for random process was distribution family, right? So for example, we said okay, we have random process, right, as a collection of random variables, yeah, and with that we said okay, the lecture before that we talked about the discrete or continuous nature of this index, and we also talked about discrete and continuous nature of the actual values. Following that lecture, after that we looked at okay, what kind of statistics is associated with the random process. So we said okay, one statistics would be how each of these is distributed, right? Each one is distributed, but that led to say a collection of distributions for this guy, this guy, this guy, this guy. But then we also needed pairwise distributions, right? So how are x1 and x2 jointly distributed? How are x1 and x3 jointly distributed? So we needed pairs. Then we also need triplets and so on. So up to n tuple. So that led to the idea of distribution family associated with a random process. And then within that we said okay, we can also look at what kind of mean values are associated with each of these processes, right? So mu x1 or e of x1, and we realize that if it is ex1, then for in general case this is ex2, ex3. So we ended up talking about the mean value function, right? Because it now became from ex, it became ext. Yeah? Unless for the special case where all of them have the same mean, that would be a special case. But the general situation requires a mean value function. Then further associated with this, we realize that there will have to be a variance function, right? So then we went from variance to the variance function. And lastly, we went to, like for covariance, we had talked about for two random variables, we had talked about what's the covariance between x1 and x2, so on. So for this guy, what we needed was something that can capture all pairs, right? So for that we came with the covariance function, which was saying that R S S T. Yeah, what was this? It was covariance of XS with XT. Yeah, and then correlation was a normalized version of this. And last time we looked at some meanings of this. What does this really represent? Also we looked at cross covariance. So this is a quick summary of what we did last time. Yeah, the whole idea, how is it connected? It is the different statistical descriptions linked to a random process, right? So the distribution family covers everything, but then as in the single variable case, it is more so in the random process, very hard to work with. So what we do, we replace with their proxy functions, yeah, and usually work with those. Okay, today we go a bit further to identify another important characteristic or types, let's say, or dividing criteria for random processes. Okay, this is one of the most important divisions of random processes. Okay, even more important than, we have divided random process before this, like as a discrete state, discrete time, continuous state, continuous time, continuous state, discrete. That was also a criteria for divided into 4 classes. Yeah. Today we will define a class of random processes that plays a huge role in a lot of work we do with random processes in the applied field, applied mathematics and statistics. Yeah. So that has to start with, as everything else in this course, it has to start with a story. Right? So the story will take us to the problem or the development of this thing. There is a saying, time changes everything. So no? Yeah, time changes everything. So basically it changes everything, yes, but almost everything. Let's say I ask two of you, yeah, to go to Gadoon here industry, and I tell you a particular industrial process, some machine, its motion or something, whatever, you have to record, say, large sample of that process. Okay. Now, assuming that there is some randomness in that process, and you are to, let's say, record n samples, 1,000 samples, 10,000 samples, depending on my requirement for this. And then I ask you to not only do that, but you go there, you collect on Monday morning, you're supposed to go there, collect this data, this process recordings, n samples, and then deduce some statistics from it and show me the statistics. What's your conclusion about this process? Okay, how do you think it is distributed? What kind of mean variances does it display? What distribution families it may have? All that. So I'll summarize that as saying, give me some statistics of that process. So now let's say one of you, so this is, let's say this is some industrial process going on, and one of you goes, the early bird gets there at 8 a.m. in the morning, yeah, and records, let's say starting at 8 a.m. this person records from xt1 to xt, let's write capital N, maybe 1,000 samples or whatever I told you to. So one of you collects these. This is an ongoing process, continuous running machine or something, and you collect these. Based on this, you are going to give me some statistics of this process. The other one, who's not used to waking up early, gets there with a delay, 2 hours late or something, yeah, and that person, that student, also collects n samples, but with the difference that there is a delay now, yeah, and with that also so the first one extracts some statistics based on this data, and the other one extracts some statistics based on this data. Now the question is, will they find the same statistics there or not? Will their conclusions, let's say about the mean, the variance function, whatever, of this process, would they end up concluding the same thing, or their conclusions would be different? What do you think?
If the industry is working on the same efficiency, I guess then there will be a same.
What kind of assumption, for example, you need to make to say that the statistics you draw from these two will be same?
If it is working with same efficiency and producing same thing, then I guess there will be no difference between statistics.
Okay. So to answer that question, that thing will be included here somewhere, but the statistics of these two, the answer to this question whether you will get the same statistics or not, the answer is it really depends on the nature of this process. The nature that we are interested in looking at is, do its statistics change over time? Let's say it's a process whose statistics do not change over time. So given a large enough sample taken at any time, you get the same statistics. There are processes like that. And then there are processes where the statistics are changing either slowly or very rapidly. So if it is the process is kind of process where the statistics change over time, then most likely these two students will get different conclusions. However, if it is a process whose statistics do not change over time, yeah, then given that the samples are large enough, they will conclude the same statistics. Okay. Now that is such a process. That is the key question here. Yeah. And such a process, we call it statistically time invariant. So its statistics does not depend on time. As an example, rolling a die. Do it today. Do it tomorrow. Do it 1,000 years from now. Do the statistics change? 6 outcomes, 1 by 6, 8. Uniform distribution, mean value you can find, variance you can find. Never will it change, right? But there are processes that whose statistics change over time also. So if the statistics of the process is time invariant, now this defines this question. Answering this question defines this huge class of processes. So there is this, these are random processes. Within it are a subclass of random processes whose statistics does not change with time. Yeah. So this is RPs, all of them. This is whose statistics are not, and we have a name for that. Okay. Stationary stochastic process or stationary random process. What is stationary? What is your shop say? What is
Stuck
it?
things,
Something stuck in, stopped, not moving. What is stationary here? It's statistics. Statistics is not changing. So these are stationary random processes. Then the rest is non-stationary. Together, stationary, non-stationary form random processes. Okay. So now, how do we then define or discuss what? Now we need to make it more formal.
So when we have a stop time, so then why we are dealing with so many times? If we know that on the second time there will be the same statistic, third time there will be the same. So no, it will not become a random variable simple.
No, we're not talking about a single point, right? We're talking about collecting a huge, like for example, rolling a die is an experiment. To find its statistics, don't you need to do it many times? Yeah.
एक दफ़ा कर लें तो सर सारी स्टेटिस्टिक हमारे पास उसकी आ जाएगी. So मतलब for one time we can discuss all of its statistics.
But when you say one time, you don't just throw it one time and get 4, yeah, and say okay. You'll have to throw it many times. That is one time. One time itself has so many repetitions. In many cases, these observations, these are kind of repetitions of this process. So of course, to get the statistics out, you have to observe it many times or over a length of time. Yeah. So we're not saying it's stationary, meaning that the process itself is stuck in one value. Yeah. We're saying its statistics are not changing. So I'll make it more formal now. But this is the whole course is actually this course. When I taught it in Sweden, this very similar course. Its title was Stationary Stochastic Processes, and actually we don't name it here like that, but it is actually non-stationary is a separate course then. Yeah. So coming to the major class here, stationary random processes. Let's keep in mind it is based on the idea that this process whose statistics does not change over time. Now we will make it more formal. What do we mean by that? So there is the concept of strict stationarity, strict or strictly stationary, SS, random process is let's say there is a random process xt, t in t, yeah, our random process, this guy. This is strictly stationary if all of its distributions, the whole family, kitni thi wo? They were the single ones, pairs, triplets, all that. The entire family does not change over time. Okay, that's why we say strictly stationary, really stationary, completely stationary. What is that? The entire family of the statistics associated with the random process is time invariant or does not change with time. In other words, we are saying that fxt1 to xtn x1 equals, you collect n samples of this process, yeah, and if you collect n samples but shifted by some time tau, okay, so the distribution of that would be t1 plus tau up to xtn plus tau. Remember, these were the two data sets that the two students collected, yeah. Their distributions x1, x2, xn should be the same. There is a question mark, okay, if they are the same. But for what? Not just anything. It has to be true for all n, single, pairs, triplets, all that. It has to be true for all t1, t2, tn within t, because of course our process is defined in t, so that is a given. And so for all of these, and for all, what's the third one?
For all n,
x2. These values? Yes. Yeah, that's also fine. And
for all n belongs to.
So for all x1 and for all, one important thing you're missing. कौन सा variable है? Which variable is left?
Joint distribution.
Joint, everything is covered by n.
Tau.
Tau, the delays.
Yes.
Yeah, so they have to hold true for all delays also. And of course, it's not any value of tau. How is the value of tau restricted? It is that any ti plus tau should still be in t, of course. Yeah, you cannot ask me to, if you choose a tau such that this value gets out of my allowed range, then I'm not required to prove anything for you. Yeah, so that's a given also. So there is a question mark. Are they equal for all of that? If they are, that's when the process is strictly stationary. This is the formal representation of what I said earlier, that a process whose statistics does not change over time. Statistics mean individual distributions, pairs of distribution, triplets of distributions. Not change over time means any shift in time would lead to the same distribution. As you can guess, this is a huge headache, right? I mean, who is gonna show all of that? So in some cases you can. So we are saying that xt, so let's say if I have t1, t2, yeah, t1, t2, xt1, xt2, xt3, xtn, and the process xt1 plus tau, xt2 plus tau, so on xtn plus tau. These two should have the same distribution families. Yeah, if they have the same distribution families, I've just rewritten this thing here just for you understanding. Remember, the first student collected this and the second collected
This.
tau was a 2 hour delay in our case, but the number of samples was the same.
The same, yes.
If this happens, now processes are not required to allow this. If they don't allow this, they are non-stationary. Okay, most processes are non-stationary. And why study stationary processes? Most of your equations and those things are non-linear. Why do you study linear? Things are piecewise linear,
Piecewise.
locally linear.
Easy to
Even
tackle.
most of this non-stationary processes turn out to be locally stationary. So we can set ranges and apply whatever methods we have developed for stationary processes to ranges. Yeah, or you could have often the non-linear methods build further on linear methods. Yeah, so same here. Non-stationary methods will start with stationary methods, try to generalize them. Yeah, so even though most processes would actually be non-stationary, but the tools we learn through stationary processes are still very much applicable, and we do use them. Okay, so right now this is strict stationary.
Yes.
Yes, very hard to work with unless you're dealing with something very theoretical. Just you've written Gaussian distributions and you try to show this in general. Okay, fine. Real life is not like that. Like the industrial data you collect from Gadoon, for example, from the industry, you will be stuck. You'll have to work with data there. So what can you do? We have already done something like this previously.
So we make a distribution of it.
Distributions are here. Yeah?
Expectations.
Yes. So remember I said the proxies there, the mean, the variance, the mean value function, covariance function for random value processes. They were proxy for these guys because they are very hard to work with. Here also we will do the same thing. We'll say okay, strict stationarity, very good, very nice, very hard. Yeah. So we will take their
Moments.
Moments.
second order, first order, second order moments. We'll work with moments and we'll say, okay, do the moments, the first and second moment of the random process, do they change with time or not? Okay, so when we go to these moments, yeah, so and I said first and second moments, then we are going from strict to,
Why?
there are multiple names, weakly stationary stochastic processes, WSS, also called widely wide sense stationary or weakly stationary.
Yes.
Wide sense means loose sense. Yeah. So true sense, this one. True or strict sense, this one. But very hard to work with unless something very theoretical. What you do, you use its proxy. You say, okay, are the first and second order statistics changing with time or not? Maybe that's enough for us. And I'll show you why that will be enough for us. Remember we said in most cases with processes, when designing based on random processes or doing things, we will make our decision based on the first two moments. If we're going to make our decisions based on the first two moments, why do I need to bother about all the other moments or the entire? If they are stationary, okay, my decisions hold, right? So, and there are other reasons I'll explain. For Gaussian processes or normally distributed random processes, if it is weakly stationary, it is also strict stationary. That's a very powerful statement. Okay, so that again brings us to the importance of this thing. Always ask yourself, what do we lose by making things easier? So if we lose, okay, are there cases where that loss isn't large? If the process is Gaussian and you can show that it's widely or weakly stationary, it's actually strictly stationary. Why is that? I mentioned something before.
Symmetrical distribution.
Sorry.
Symmetric distribution is good.
No, symmetry is not the thing. Remember when we wrote the moments?
Yes.
We went up to second moment. Then I said there is third and fourth moment and so on. For Gaussian, I mentioned something about the higher moments. For Gaussian distribution, all the higher moments beyond second can be written in terms of the first two. Once you know the first two, you know the entire Gaussian distribution. Third moment, fourth moment it is not generally true. Even when you write the formula of Gaussian distribution, you are mentioning mean and variance, only the first two. So if they are not changing, why would the process change? So then it will be strictly stationary. But coming back to this, the idea of using a proxy for this thing, and sometimes we also call it second order stationary. Yeah, second order. Why second order? Because mostly we go up to mean and covariance or variance. Yeah. So second order stationary. Now how do we define that? Yeah. This is in words only. Instead of looking at the entire distribution family of the random process being stationary, which would make it nicely strictly stationary, and as independence and correlation, strict stationarity always implies weak stationarity. But weak stationarity does not go back. Okay. So now coming to the weak stationarity, wide sense stationarity, whichever second order stationarity, whichever you like to use. How do we define that? Let's see. If you recall the industrial process that you were to measure, let's say like this, x 100, x101, and so on, x106, and so on. Now this was your industrial process going on. Yeah. Now I'm going to write something and then we can discuss it. What would weakly stationarity mean? Let's say that the mean of each of these is the same. That is, let's say the mean, remember we had written last time the mean and function, but now we're taking away t. What are we saying? That the mean is time invariant. Yeah. So let's say if this holds, that the mean is time invariant, it doesn't really matter. Each one has the same mean. And let's say the covariance of x1 with x2 equals the covariance of x2 with x3. That all of them equal covariance of xt with xt plus 1 for all t. What are we saying? That adjacent pairs always have the same covariance. Doesn't matter where they are. So x1 and x2 are adjacent. Whatever covariance they have, x100 and x100 101, x100 and x101 will have the same covariance. Meaning what? Doesn't really depend where they are in time. The only thing that matters is how far apart they are from each other. Yeah. Same thing for our, let's say, x1 with x3 is the same as what? So values that are 2 units apart always have the same covariance. These two don't have to be equal. Yeah? What has to be equal is that the index doesn't really matter. It's their difference. That means you're taking away the actual t value. It's only tau, the difference, that is defining how they are correlated. So xt plus 2 for all t, or in general Rxt1, covariance of Rxt1 with Rxt1 plus tau is the same as covariance of Rxt2 with Rxt2 plus tau, and so on. Yeah, I've written this for all t and tau. Again, now we have written all of these will be covered in here. Yeah, we could make it just make it ti, and then everything will be covered. All of this is saying what? In a nutshell, it's saying that the actual t, was it 8 a.m. or 10 a.m.? The actual t doesn't matter. It's the difference or the gap or the delay between the two values that defines their covariance or correlation. So actual time or location does not matter. If these two hold, both of these hold, then we can say that the two guys that we sent to study, if they are just focusing, now before I said find the statistics, yeah, now let's say as we in practice we focus on the first two moments. Now these two guys, they got these data sets which were tau apart, but they were finding the mean and covariance function of the data sets. If these two hold, what would your answer be? Would they give me the same statistics? For these two values, they will give me the same functions, right? So the first one will say the mean is this. Why? Because if this holds, the mean is time invariant. Yes. Then the first one will say the covariance function between first and second, first and third is so and so. The second one will say the covariance function between first and its delayed version, whatever that is this, and delayed version is this. So they will give me the same, very same statistics. All the values they will give me will be same. Notice we're not saying that this has to equal this thing. Yeah, we're saying this has to equal x2, x3. The same gap, that is important. Yeah. So if these two conditions hold, basically these two sets of conditions hold, then as far as the second order statistics is concerned, the process does not care. Yeah, it is time invariant, and that is what we call the weak sense stationary or wide sense stationary. And as I said, strict sense stationary applies, wide sense stationarity, while the converse, if you know it's wide sense stationary, doesn't have to be strict sense. It doesn't generalize that way. Then as I've already said, why use it, why work with it? Firstly, we already work with first two moments in most of the cases. So why not just check them? Do they change over time? If they don't change over time, okay, that's this is good enough for us. We don't have to go here. Second, as I said, the normal process, the Gaussian process, which is very common. We will come to that, the central limit theorem and all that. So being very common, it has a lot of applications. And for the Gaussian process, in fact, the converse also holds. Okay, only for what? Gaussian process. So, of course, and this is a very important process. We will see it later in the next module when we go to different types of different common random processes. We'll see it there. So together these things help us. Now let's write this thing in a, this is more spread out, yeah, just for explaining sake. Can we write it in a more succinct way, more efficient way, how to define wide sense stationarity now? So now I will write the formal definition. We wrote the formal definition of strict sense stationarity. Remember the whole family thing being equal. So a random process xt, t in t, is WSS. It has to meet three conditions. Has constant mean. That is MXT is M. Okay, has to have a constant mean. Second,
Gap difference.
its covariance
Time difference is same.
function
Dependent on time.
RST depends on what?
Time difference.
Yes, how do we write it now? We're writing mathematics now. Depends only on what?
Time difference.
Tau.
Yeah, what is tau?
Tau.
Time difference. I think.
Time difference.
Yeah, from here, what is tau? Let's say the way we note it as is smaller than t.
T minus S.
T minus s. Yeah. So the covariance function depends only on t minus s. What does
Okay.
it say? What is it saying? I don't care what time exactly it is, 8 a.m. or 10 a.m. As long as the difference between them is this is 8, this is 8:15, this is 10, and this is 10:15. As long as the gap between them is the same, the covariance will turn out to be same. Yeah. So it does not vary. So why am I saying it doesn't depend on the actual value of the time? Let's say this is 1 and this is 4. Yeah, you get some value. 4 minus 1 is 3. Yeah. If this is 2 and this is 5, 5 minus 2 is also 3. So that should be equal to the original 1 to 4. Yeah. So third one is more of a mathematical formalism. And these two are the real conceptual deals. The third one is just saying that the covariance function and covariance function is finite for all S and T. Okay. Why that thing? This is just mostly formalism. The issue with this one is if it is at some point it becomes infinite, there are some distributions that will have this issue, then you won't be able to prove this. Okay, that's the only issue. Yeah. So not really conceptually for us. Many times we just skip this one, by the way. Yeah, but just since you guys are from math side, so you will appreciate it. Basically, the concept is here. And then this will ensure that you are able to test what we told you to test. Yeah. So now we can change the notation. Yeah, a notation thing now, a very important thing. Notice this one. If a process is White-Sands stationary, we know that S and T don't matter. Yes. What matters is their difference, tau. So we change the notation for White-Sands stationary processes. We, instead of using two variables, we just use one. This is abuse of notation. Yeah, the same function sometimes appears with two variables, sometimes it appears with one variable. Now what does that mean? Just keep this in mind as a convention. When it appears with one variable, we are saying either we have already proven that it's a White-Sands stationary process, so we don't need the two, we just need the gap, or we have assumed that it is White-Sands stationary, so again we don't need these things. Yeah. When we write two of these, we are saying things are still open. Neither we have proven nor we have assumed that this process is White-Sands stationary. It may be non-stationary, it may be White-Sands. Once you either prove or assume stationarity, you are allowed to use R tau.
It means then we are going to strictly stationarity after a first notation, because we have proved that it's a White-Sands stationary, then we'll check up to strictly.
No. If you have proven that it is White-Sands stationary, that means at least this thing holds. Yeah. So you can replace S and T with just a tau. Strict stationary would require you to either prove that all the higher moments are also time invariant, or it will require you to prove that all the families, the entire family is stationary. Yeah. So it's just saying for a general random process, what is the covariance function? This thing we have written it. Yeah. But once you either have proven or assumed that your random process that you are working with is wide sense stationary, then you can assume this. If you have even proven or assumed strict stationarity, you can still do this. Why? Because strict stationarity always implies wide sense stationarity. Yeah. So what does that bring bring us to? So remember, what was RST for us? It was covariance of XS with XT. Yes. Now, if here is this assumption that the process is
stationary.
at least weak sense stationary, it is strictly stationary, then you can still go there. Then we know that the covariance of this is the same as S plus tau. Here we are calling T as S plus tau. Then this thing can be written as covariance of what? X0 with what?
X tau.
X tau. If you have assumed stationarity or weak sense stationarity, the S doesn't really matter. It's the tau, because the gap here is tau. Gap here is tau minus 0, tau. So that means one of the variables is redundant now. As soon as you bring in this information, before this information both variables are needed. After this information comes in, one of them became redundant, you can just lock it. So which is left? Tau, just one variable. Yeah. So I could call it R0 tau from our old notation. Why do that? Why not just go to a simpler notation? Okay. Now remember, if somebody gives you a covariance function and it has only one parameter, know that they are assuming
Two
stationarity,
stationary.
or at least wide sense stationarity, right? So from here on, this is what we will also do. For us, the process will be R tau for wide sense stationary processes, right? And if it is not, then we so there are some important properties. Before that, let's see the covariance function. This guy, the R tau thing. Can you tell me what this is now? R tau is covariance of xt with xt plus tau.
Time.
Yeah. So from now on, for wide sense stationary processes, let's say this is the process. When we say tau, we mean take any xt and then any xt plus tau. This is the covariance between this value and this value. That's what we are looking at. And because of stationarity, that is same as, let's say, xt prime and xt prime plus tau. Because so the covariance between this point and this point is the same as the covariance between this point as long as they are both delayed by the same amount. Okay, so covariance. Can you write this? By the way, what does this come to? If we write it out using our definition, what is it?
Expectation of X.
X
T
minus
mu.
mu. Which mu? The mean of this or this?
Mu t.
T plus
T. Yeah, and this is wide sense stationary. So do we need a tau or no?
No.
No. Yeah. The process is wide sense stationary. So yeah, in reality it should be mean of t and here mean of t plus tau, but they're the same. It's
Yes.
wide sense stationary. So I can just write m. Yes, and
Yes,
this
yes.
becomes xt plus tau minus m. What does that come out to? You can calculate it or rewrite it to get. Why am I writing this? Actually, I want to show you this thing. What is R0 then?
Will say
R0?
tau 0 कर देंगे
क्या
expectation
क्या बना?
t square minus m square हो जाएगा
वो क्या होता है?
m square ये मतलब
Variance.
variance it's variance of t
Right? It's the variance of
function of t variance.
t. But notice that the variance of each of these xt is not a function of time. It's just R0, one value. What does that tell you? So for a wide sense stationary process or a strictly stationary process also, the variance function is also independent of time. Remember?
Variance function is also independent of time.
Yeah. Remember we had the mean value function, variance function and covariance. For wide sense stationarity, what did we work with? Mean, and the mean value function collapsed to this one value. The covariance function did not collapse, it just got rid of the time parameters. Yeah, but a necessary result of this second and first thing together leads us to this thing. Why are we saying Vxt is independent of time? We're saying for any t, variance of x1 has to be R0, variance of x2 has to be R0, variance of x3, whatever value this is, there is no time here. Do you see any time here? This is one value. So this is, although this is not in the test, we didn't write it, but this is also a very good indication. Often if you don't want to test the covariance, first test would be check the mean, check the variance. Are they changing with time? If they are changing with, any of them is changing with time, this process cannot be wide sense stationary. Okay. If both of them are constants, then go for the second test on covariance. So sometimes it helps when you solve the problems also. You will find that the solution is simpler if you first check this instead of trying to prove the covariance being independent of time. Yeah. So that is this thing. What about the correlation of a wide sense stationary process? What would that become now? Rho t, rho tau. Remember rho st, what was it? Was normalized, yeah. St, what was it? It was r st divided by square root of rs and r t. Remember? So now what would rho tau be? Any guesses? R
of
tau
divided by
interesting is it?
r of t, x of t.
tau की value निकाले.
First let's say remember this was what? This was variance of s, yeah?
Yes.
This was, sorry, variance of x s, and this was variance of x t. Yeah, when we took tau we said this is 0, this is tau, and so we are talking about variance of x0 and variance of x tau. Yeah, but that can be written just like this. That can be written as r0 and r tau. Agreed?
Yes.
For, let's see, r0, yeah. So variance of x tau, but that is not this hang on, sorry, this one, variance of x tau, it's not r tau, right? It is r0. right?
Yes.
Yeah. So then it becomes or simply over. Yeah, it
Yes.
becomes simpler. Again, the whole thing collapses to a single variable. Yeah. Here again we have this thing. Remember, if it is white and stationary, necessarily its variance will be independent of t. So that means whatever this has, whatever variance this guy has to have the same variance. And we found that this thing was R0, then this thing is also R0, right? The gap is 0. Okay. So should we do some important properties or leave it for next lecture? Leave it for next. Okay. So that's it for today. There's a lot to absorb here, but if you just summarize it on your own, you will find that it's not really, once you understand it, it's not too much. The whole story is this. There are random processes whose statistics does not change over time. Yeah, that means those processes, if you observe them for a reasonably long time now or for a reasonably long time with a delay, the statistics you draw will be same. If all the statistics you draw are same, they are strictly stationary. Strict stationarity, headache to work with. You can try to say, okay, I'm not concerned about all the statistics. I only want to see the second order, first and second order statistics. Are they stationary, time invariant or not? If they happen to be time invariant, then you say that my process is at least weakly stationary, and that's good enough for me to work with the first two moments. And for that, what were the conditions we defined? Finally, formally, the mean should be independent of time, and the covariance function should depend only on the gap between
Time
s and t,
differences.
meaning should depend only on tau.
Yes.
Yeah, and the necessary result of both of these was that the variance will also be, we did not put variance as a test,
Yes.
okay, but the necessary result of the test is that the variance will also be independent of time. Okay, so basically this kind of summarizes everything we did. Okay, so then you'll practice and learn to use it in analyzing your processes. Next time we will look at some properties of our tau. What can we say about this function? Remember when we defined the expectation operator, we talked about its properties, we defined variance, we talked about its properties. Now we have a new function which is the covariance function of a white and stationary process. Yeah. So what properties should this guy satisfy? Okay. So next time we will do that, and with that we will also because that's just I think one sheet with me, so that won't take very long. But then in the next within the next lecture we will start our journey into, that will be our next module. So I don't know, yours is the fourth module or something, then the fifth module, which is common random processes. I mean, that we haven't actually, I mentioned Gaussian from time to time, but I haven't defined it. Yeah, we will see like 9 or 10 of the most common random processes.
Yes.
This will cover Markov also, Wiener, Brownian motion, all of that. But if you have a firm grasp on all of this, those are just like, you know,
Levy walks.
yeah, OBI. Okay, so let's close this.